Some questions just came in from Emily in regards to all of the careful suspension tuning that I've been doing on my Tesla Model 3. So it's a very unique car situation. And recently I have tested every single spring rate in this true coilover system, meaning that the car originally had a separated shock and spring in the back, like many modern suspensions have. And for the maximum amount of spring choice and ride height adjustability, we always convert every single car that has a separate spring and damper into coilover damper in the rear, and all cars have coilovers in the front. So anyhow, I think I've frustrated Cam in the shop so many times because he's busy on the welding robot. He's busy helping Tommy pack up boxes before the shipping companies pick up. And I've always got some agenda or some level of dissatisfaction or some other setting that I want to try on the Tesla, because it's just like we're in no man's land. There's no good example of any other company setting up a car like this. Anything that's available for that car right now, it's just going to be like a shock and a spring with a little spring perch on the rear lower control arm. So no information out there on coilovers. You can go online and you can key in all sorts of information into a spring rate calculator, but that might get you in the zone, but you really need to feel it out. So back to Emily's question, what is the difference between having preload versus no preload on the spring? She would like to better understand how preload affects ride quality, suspension behavior, and overall handling. So generally on most coilover applications, we have pretty stiff springs. We're a company that specializes in serving our core customer group, which is low style drift cars. So generally, if your car is slammed, then you want a pretty high spring rate just to keep it from scraping. And cars that we're used to working with, S-chassis Nissans, even Z33, very popular applications, FRS, BRZ, they're all lighter than the Tesla. So in addition to all that, we've got a car that has the battery as the lowest point on the car, whereas most cars have maybe the exhaust pipe is the thing that's going to scrape, maybe even the subframe or the frame rails, hopefully not the oil pan. And in notorious cars that have oil pan problems like BMWs, we do have a super thick aluminum skid plate. But when it comes to the Tesla, basically you're more or less scraping battery, or hopefully maybe just like the jack points. But those points underneath the car, they can only take so many times of getting banged up and scraped before there's just no restoring them. So anyways, back to the question, how preload affects ride quality and suspension behavior. I think the most simple way to put this is that if you preload the spring, then you're going to get the compression stiffness that is in between spring rates. So on the low end, the springs that we offer are 5, 6, 7, and 8 kg. Then they jump 2 kg, so 8, 10, 12, 14. And then on the high end, they jump even more. So we might go 20 or 22 to 30 or 32, and then 50 is the stiffest kg rate that we offer. So if you're trying to decide between maybe an 8 and 10 kg, then you can basically preload the 8 kg, and the kg rate on springs, it's actually like average stiffness. So all the springs that we sell, they are linear coilover springs. This is the most popular spring to run on track. Linear spring rate means that that rate increases in a linear way from when you start to compress it to the coil bind. And the number that pops out of the spring rating machine is simply the average through that spring's travel. And by the way, if you want to find out how much travel a spring has until coil bind, then basically you would just take calipers and you would measure the free space in between each coil, and then you add all that up, and that is the spring's maximum travel until bind. So if you're really doing a good job at choosing the right spring, you will not only choose the spring rate, but you will also consider how the spring's airspace in between the coils compares to the maximum travel of the shock shaft. And additionally, you will consider your bump stop height and match all those things up so that the bump stop is actually doing its job. You will also want to consider at what point in that shock shaft travel and that springs available travel is the car sitting at static ride height or at rest. So this now tells you how much up travel and down travel is available. So the typical customer running a slammed car is going to choose a pretty high spring rate for that car. And that means that his static ride height is going to exist somewhere near the top out on that shock. So there's actually an internal top out stopper. It's a pretty small disc. It's not as forgiving as the external bump stop, which we use microcellular foam bump stops. They're progressive in nature, so they're pretty gentle when you first get into them, and then they just ramp up the stiffness until it just stops the suspension travel. And these are stackable, so you can really tune in these lengths. So the spring, the shock shaft, and the bump stop stack height. And the actual ride height is mainly adjusted in the threaded connection between the fully threaded damper and the coilover lower mount. So initially, our advice is to basically do zero preload on any spring because we already ship coilovers with pretty high spring rates. And so to get the best ride quality with a higher spring rate, you don't want to ramp that up anymore. And therefore, zero preload is going to be just spinning up the spring's bottom collar until it touches off on that spring. But when the car's up on jacks, you can just grab the spring and twist it back and forth easily, meaning you can't move the spring up and down, but you can spin it. So there won't be any extra noise. The spring won't be falling out of its seat as if it was drooped. It's going to be secure, but there's going to be no pressure exerted on that spring by cranking the spanner wrenches and that lower spring perch. So circling back around how preload affects ride quality, basically if you had an 8 kg spring and you felt like, oh, maybe I have a little bit too much body roll, or maybe the car's lacking steering response, but I don't have the money for sway bars right now, then you can just crank some preload into your 8 kg spring until the average rate on that spring is somewhere around 9 kg. And if that suits your agenda for having a track day and you've got the steering response and you've got just the right amount of body roll by cranking in a few millimeters, or if you get pretty aggressive, maybe like 10 to 12, you'll feel how much pressure you're putting on that bottom spring seat because that rate cranks up in a way that you can definitely feel. You feel it in your hand, in the spanner wrench, and you can definitely feel it as soon as you take it out on the road, start turning the wheel back and forth, kind of feeling that body roll. You can slam on the brakes to test dive. You can just gas it and see how the car is squatting. So this is the kind of thing that gives you the feeling of the ratio and stiffness between the back of the car and the front of the car. Just full power squatting, full brake dive, and you can control that front to rear ratio very well with your spring choice and with the preload setting. In addition to that, I always like to take the car over speed bumps because I think that it's a little bit more clear of an indication about the stiffness between front to back. Because unlike throttling the car down the road and doing fastest possible stop to evaluate the squat and the dive under braking, just jamming through speed bumps is just like a boom comparison between front and rear. It's so much more clear than than that other method that I was talking about. But the car should be evaluated in all ways, from body roll, braking dive, squat, and behavior over bumps, and also holes. So kind of a recessed manhole cover on the street. So that's like a negative bump and positive bump on a speed bump. I think that's a really good way to evaluate how your preload is affecting the ride and handling and steering, and that'll help you make a good choice about your preload. But initially, we want the most traction by maintaining that suspension sensitivity by at least starting out with 0 preload. So regarding the Tesla coilover spring settings, Emily's question is, when you tested different setups, you mentioned that during braking in the front of the car, it noticeably dives. It often indicates that the front spring rate, if it doesn't dive, might be too stiff, or if it dives, the spring rate might be too soft. This is true. In my personal testing, going everywhere from 14 kg to 6 kg in the Tesla, in a very heavy car, in the quest of making sure that this car is a very good daily driver, and you can give anyone a ride in that car, including my parents. And if they don't notice that anything's too unusual, then I think that the coilovers are riding very well. And that's the progression that I've gotten with that car. And when I got into a 8 kg front and 6 kg rear, the car was so buttery, but there was a noticeable amount of dive, noticeable decrease in steering response, and a noticeable increase in body roll. Now, in the Tesla, because all the weight is down low, it's really quite a bit less body roll than most cars that are much more top heavy with their, most of the weight in the engine is above the axle. Anyways, about me noticing that the front of the car noticeably dives, indicating that the spring rate is too soft. In this case, many people might choose to either increase the front spring rate or even adjust the front damper, but they often overlook the effect of the rear suspension. So Emily asks if I can elaborate on how adjusting the rear spring rate or preload or damper can help reduce front-end dive during braking. She'd like to understand more about the relationship between front to rear balance and the controls that we have over that. So this is a great question. I'm glad that she was listening to me on my test drives. So basically, if the point of my project is to have both a very good daily driver and an awesome car on the track, and there's a noticeable amount of dive, what I can do is I can simply go to the rear shocks. There's a rebound adjuster on there. And when we turn that from full soft and we start cranking in some clockwise adjustment on that adjuster, basically we're getting rebound resistance. In other words, we are resisting the rear end's ability to come up out of the suspension. So if you think about what happens during braking dive, the front goes down and the rear goes up and the weight shifts forward. So if you don't want the weight to shift too much without buying any other springs and completely redoing your suspension and your ride height and buying stuff, all you have to do is jack up the car, reach your arm over the rear tire in this case, and crank in some clicks in the clockwise direction and redo the test until you're satisfied with a reduction in dive. That is simply on the rear rebound adjuster. Similarly, as far as wanting to get more squat in the rear, so a rear weight shift, if you've got a powerful car and you really want to put that power to the ground, the great thing about rear-wheel drive cars is that the weight naturally shifts to the rear when you slam on the gas. So if you want to increase your grip level in the rear, then you would want to decrease the setting on the rebound adjuster on the front shocks. So when you decrease the rebound resistance in the front, that promotes the front end to come up when the gas gets slammed. And if you want to increase the squat in the rear, then you will want to use a lighter spring. If you want to promote squat by a front spring rate change, then you would actually make sure that you're using a stiffer spring in the front. So the spring is a compression resistance, and the flip side of that is that it'll actually promote the car raising up out of its static ride height. So if you want that front to lift, you want the weight to shift to the rear, that's why you would increase the front rate, decrease the rear rate. And again, for promoting squat, you would put the front on full soft on the rebound resistance, allowing that car to come up and shift the weight to the rear. And the rebound setting in the case of squat in the rear, it's not really a factor. Just the spring rate is a factor in squat. So I want to speak to the methodology in this spring rate choice on the Tesla, a car that is very heavy, because I knew this car is heavier than any other car that we've tuned coilovers for. That made me start out on some pretty high spring kg rates. I've been informed by my previous experience with Lexus GS. That's daily drivers that I've had in the past that are pretty heavy, and they've had some pretty high rates. This particular car, actually, the Tesla Model 3 has a rear weight bias. So in that way, it was like a no man's land. And of course, the true rear coilovers are also something that's very unique. So I started out with some pretty high spring rates, like a 12 and 14. And I gotta say, the ride was totally punishing. I borrowed some coilover upper mounts from another brand of coilovers, and this is the first time that I've ever experimented with a rubber bushing in the upper mount. And I thought it's important to at least try this because this electric car is an absolutely quiet car. And if that's why people bought the car, I think that they might find the noise transmission that exists in the standard pillow ball, spherical bearing upper mounts that we use in every single application. I think that they might not like that added noise, vibration, and harshness getting transmitted through the chassis. So I started out with rubber upper mounts. And just to cut to the chase about what I found out is in testing all these rates, I did it all within about 1,000 miles on the car. So when I finally got my prototype upper mounts, spherical bearing, to put in the car, and I took off the rubber bushings, I noticed that they were very deformed and they had cracks formed in them. And this is only in 1,000 miles of driving. So I haven't gone and read any customer reviews on other companies' coilovers. It's just forming my own opinion on these things. But I imagine that there has to be some reviews out there that people are needing to replace their coilover upper mount bushings very frequently. I just can't imagine that anyone even goes and checks them by 1,000 miles, but when they do check them, I imagine that there must be some state of destruction in those rubber upper mounts that is much more extreme than the deformation and the cracking that I observed. But eventually those things are gonna die, and the condition that those were in under 1,000 miles was not good. In addition, I was kind of surprised at how noisy the rubber upper mounts were. And although the spherical bearings do transmit some texture in the road, I think that really informs the driver about what is happening with the grip across different kinds of surfaces in the car. So I think the thing that is so uninteresting about electric cars for sports car guys is that they're just totally dead. You're going down the road like you're playing a video game. And I think it's really important for traditional car guys to get that driver foot back in the car. So basically, we're selling an entire line of parts that consist of solid bushings, bushing to bearing conversions, and we're eliminating every single piece of rubber in the suspension and the drivetrain with solid subframe bushings and solid rear drive unit mounts. So the subframe and rear drive unit solid mounts, this allows you to actually hear what your powertrain is doing. So this lets you hear the gear lash. This lets you hear the differential working. And I think that when the car really is putting the power to the road, I think that it makes a very satisfying noise. And I like to amplify that. I like to feel what my car is doing, and I like to hear it putting the power to the ground. And that's exactly what this all solid mounted suspension is doing. So I'm really pleased with the results of that. And I definitely feel more smoothness and more control and just less wonkiness and less unusual noises with the all spherical bearing coilovers versus the rubber mounts that I was using. I want to describe the methodology that I used when going from a very high rate to a very low rate and everything in between. I want to describe these steps to you because I want everyone to know what is appropriate to pair with a high or low rate spring or everything in between. It's not just about purchasing some stiff springs, but it's about knowing what's going to happen when you put that in the car. So you put a stiff spring rate in the car and you're basically riding in a static ride height position that is totally biased towards topping out the shock. In extreme situations, we've had people actually destroy the internal top out stopper. It just gets beat up so much that that damaged material would eventually get stuck in the valving of the shock. And when there's debris in there, it's kind of like the shim stack on the shock piston is stuck in a permanently open position. And basically, it just feels like you don't have shocks at all. So since we have such a huge variety of spring rates that you can put on any of our coilovers, in the description on the coilover spring page, we want you to know that you should pair that with a helper spring. So the helper spring is something that is maybe the least understood aspect of coilover suspension. Earlier in this episode, I was describing how choosing your spring length by measuring the free airspace in between each coil and knowing the compression distance until you reach coil bind should be paired up with the length of your shock shaft, or at least the exposed shock shaft in between your bump stop and the upper mount. This is why when you have a very high spring rate that basically can't really compress under the car's weight, at least not very much, you should pair that with a helper spring. This takes a high spring rate and it allows the car to sit somewhere in the middle of shock shaft travel. So when you go through driveways and you need one of those wheels to drop out to maintain traction, so when you're in an unweighted state, three-wheel motion, when you're going up the driveway, if you don't have helper springs, you will literally be three-wheel motion and one of the wheels will just be spinning in the air. And if you don't have proper differential in the car, then you're basically just stuck teetering and you can't even get up the driveway until you give it another shot with some momentum. So you can imagine that this would just be a silly thing to do if there was a bunch of traffic and cars are waiting on you. You're just going to look like a fool if you have like extremely high spring rates and no helper spring. So when you put the helper spring in there, that lets you sit in the middle of your suspension travel, not topped out on the shock. And when you sit halfway through the suspension travel and one wheel becomes unweighted, now you have the down travel in order to let that tire make contact with the road again. So that's exactly what I did on the Tesla. I wanted to make sure that I could get up my own rather extreme driveway at my house. And so I knew that if I didn't have too much compression travel with the high kg spring rates, I knew I'd have to put in that helper spring. And it worked. The car had much more travel than if I didn't have the helper springs. And on my personal driveway, I definitely need all the help I can get there. So as soon as I started to make significant changes in dropping the spring rate, then I was monitoring very carefully what position in the shock shaft travel static ride height was in. Simple way to monitor how much of your suspension travel you're using over bumps is just to put a zip tie on the shock shaft, and it'll just get pushed up and it'll stay in whatever position was the most bump that the car had seen on a test drive. So very simple, just a zip tie on the shock shaft. In regards to the helper springs, when I dropped the spring rates, I would maintain the helper spring, but because the mainspring was able to compress so much more on a middle spring rate versus a high spring rate, then it's kind of taking care of the car approaching the middle of shock shaft travel in the mainspring. Therefore, you need less help from the helper spring in order to let the car sit halfway through travel at static ride height. So this is when you crank in some preload to the helper spring. It's not really preload because the helper spring is a 3 kg spring rate, and basically it just lives its entire life completely clapped out. That's why the coils are very flat, because it's meant to live all day long, every single day, under the car's weight, being fully compressed. And the only thing it's helping you do is it's just helping the car sit at static ride height halfway through suspension travel. So when we drop the spring rate, spring is doing some of that on its own. So we crank up the bottom collar. It's not effectively cranking up the spring rate like I described earlier in this episode. It's not really spring preload. You're just taking out some of the airspace that exists in between the helper spring coils, because the mainspring is softer now, and so the car's weight is making that mainspring compress a little bit more. Additionally, when I started to significantly drop the spring rate, I started to increase the progressive bump stop stack height. So I've experimented with anything between 1 and 5 bump stops stacked on top of each other. The logic there is that if the progressive microcellular foam bump stops ramp up the rate, then on small bumps where the car is still able to exhibit a lot of bump sensitivity, maybe just going down the road on the way to work and on the way home, then it would maintain that bump sensitivity. But if you were to jam through a speed bump, or you just come across an unexpected bump in the road, then the lighter spring rate would be bolstered from just blowing through travel by having additional bump stops in there. And I figure because it's progressive, that means when you first start to compress that bump stop stack, then it's just adding a little bit of resistance. But if you were to completely blow through the lighter springs travel, then now the car would be held up and would prevent a harsh sudden bottom out by supporting the car's weight. But what I found is that when we increase the driver feedback through having all the rubber bushings in the car eliminated, even a cushy stack of bump stops is actually pretty noticeably ramping up the rate. So as I went to the lowest spring rate, I definitely went back to one single bump stop, because the car was sitting so much lower into the shaft travel at static ride height by compressing those light springs that it puts that single bump stop closer to the spring top hat where it can actually do its job. Additionally, as I went from high to medium and I compressed that helper spring halfway, now when I went from medium to the lowest spring rates on a heavy car, I totally eliminated the helper spring. But what I also did is I dramatically increased the length on those light springs. So the heavy car would compress the light spring so much that without a helper spring at all, the car would be sitting right in the middle of shock shaft travel. So I went from 180 millimeter length springs to, on the hard kg rates. I went from 180 millimeters to 250, at least in the rear. So currently my softest setup is 8 kg 200 length in the front, no helper, and 6 kg in the rear, 250 length, no helper. And that was coming from a 150 length. So in the end, with 8 and 6 kg on the Tesla Model 3, I've actually created a super buttery ride, and it's a cheaper set of coilovers because it just doesn't require the helper springs. With 0 rubber bushings in the chassis, drivetrain, and suspension system, all of these changes, from clicks on the damper to spring rate changes, they're all very clear because that suspension is not getting masked. That suspension character is not getting absorbed into those rubber bushings. Similarly, you have to consider in your general ride quality, this is very much going to have something to do with the aspect ratio of your tire pressure, the stiffness difference in sidewall of all-season tire versus summer sport tire, different brands. So there's a lot of things to consider, but I love being able to isolate the perception of the ride quality in the car to coilovers, which you have absolute control over. Part of the control that is very unique to Part Shop Max coilovers has to do with our ultra high range adjustable dampers. This is a very unique and I believe revolutionary thing that we developed. We developed this shock and its adjuster using physics models, MathCAD, some sophisticated geometry and engineering, machining, CAD design. There's really a lot that went into the design of this damper. My dad was heavily involved in that project. He was running the MathCAD models. He's an engineer that is trained in physics and thermodynamics. And using his information, we were able to design a parabolic adjuster needle. It gave us a shock that is an extremely high range of adjustability, which is right there in the name, ultra high range adjustable damper. But really the special sauce in there, besides having the ability to freely swap spring rates, having such a high range of adjustability, the really special thing is that we dropped off all of the compression resistance out of that shock. Most shocks, when they're single adjustable, when you turn the knob, you're actually adjusting compression and rebound at the same time. So even though it's really a rebound adjuster, when there's a bunch of compression resistance built into that shock, then as you close that port orifice, that oil is flowing around the needle, you're definitely affecting the compression side. But we have near 0 compression resistance in our shock, so that on a single adjustable coilover that costs under $2,000, you can still have absolute control over compression resistance by swapping springs, versus coilover that would have compression and rebound adjusters on knobs. This might cost you between $3,500 and sky's the limit. But on cars that we set up in Formula Drift that have Penske triple adjustable reservoirs, that's in the $5,500 range. And those features exist on coilovers up to $10,000. But for most of our applications that center around maybe somewhere around $1,300 in an all spherical bearing, billet aluminum coilover with full adjustability, the ultra high range damper is really a treat. It addressed all of the custom requests that we would get. The phone would ring, hey, I want my car to ride like this. This is the ride height that I'm looking for. Can you do custom dyno tuning? And we have a shock dyno in-house. We've got a shock room specifically set up to tear down and rebuild coilovers, restack the shims on the damper piston. But ever since we came out with the ultra high range adjustable damper, that was just no longer necessary. With the turn of a knob, you can accommodate any spring from 5 kg to 50 kg. And when you're choosing a number of clicks that you're adjusting into this thing, you need to keep a couple things in mind. All coilovers out there, unless they have a very carefully engineered parabolic needle in their adjuster, the character of those adjustments from full soft to full stiff, that range, first of all, it's a very narrow range. Second, the clicks in coilover adjuster are simply a tactile feedback for you to know how far you are in between soft and hard. On ours, because it is such a high range damper, you definitely need to start off on the soft side so that those things aren't just rocked out in certain applications. And only if you experience too many oscillations after going over a bump would you actually start to crank in more rebound control. So there's some guidelines. There's a tag that we include on every coilover that has advice on starting off with 0 preload, giving position in the adjuster that might be appropriate for different spring rates. Of course, every car is going to be different because there's a different weight on the car. And if we are adjusting rebound resistance, we need to remember that very heavy cars like the Tesla Model 3, the weight alone in that car is rebound resistance. So to cut to the chase on my Tesla Model 3 settings with the 8 and 6 kg spring rates on an extremely heavy car, it's really pushing it. Having a heavy car on light springs, that is its own rebound resistance. So currently around town, my car is on full soft front and rear. And it's so buttery, and it's easy to click in some stiffer shocks when I'm at the track, just with the turn of the knob. So there is 32 clicks available, and one of the most special things about the ultra high range adjustable damper is that rebound resistance in between each click is a completely repeatable amount of rebound change in between each click. And this is so far from the case of every coilover out there, unless it has a very carefully engineered adjuster. So if you take 90-something% of coilovers out there and you run it through the shock dyno on each and every click from 0 to 32, you'll find that basically there is no perceivable state of change when you're riding in the car on the first 6 clicks and the last 6 clicks. In other words, the difference in rebound resistance of the first part of the adjuster and the last part of the adjuster, they're all stacked on top of each other. So basically, if you've got 32 clicks and the first 6 and the last 6 do just about nothing, now you've got really a 20 click coilover. Then in the next 6 clicks, the mid-range setting, that starts to have dramatically more effect until you reach the middle of the adjuster. So if we chop off another 6 clicks, then you're down to 8 clicks in the very middle of the adjuster that really do a lot. So you got to keep this in mind. Basically, you got 32 clicks, and in everybody's mind, they're like, that is so much adjustability. But the range of adjustment is really built in to the internals of that shock. And 32 clicks actually means nothing. On most brands, it's kind of like you got 8 clicks that you can totally feel the difference, and then all of the rest of them just fall off towards full soft and full stiff until you just can't tell the difference. Ultra high range adjustable damper from Part Shop Max. On the shock dyno, it is an absolutely even amount of spacing from 0 to 32. So what this allows us to do is it allows us to let the customer customize their spring rate without a rebuild and a dyno tune. So this level of convenience in customizing the coilover to your use case and your liking it's absolutely amazing. It'll cost you $0 to pick out whatever spring rate you want. We definitely have done a lot of testing. We pre-package the coilovers with our favorite spring rates, and we sell coilovers in different flavors. We have a comp coilover for most drift cars, which has pretty significant spring rate on there that would allow you to slide the car easily, run the car really low. I think this is what most of our customers need, at least if they have a low power car. We have a pro coilover, which drops the spring rate down, adds grip into the car that all high power cars need. And then we have a VIP coilover. And this is for the stanced guys at the car show, running amazing fitment, beautiful 3-piece wheels, and you can barely fit your shoe underneath the car is their static ride height. So we have one shock that can serve that super diverse crowd, and you can start off your build in one direction and you can actually transform it to another direction if you change your mind. You can always just swap springs, you can add in helpers, you can adjust your bump stops, and you can make any of our coilover applications ride however you want. And I have to say, in the case of this progression in my Tesla Model 3 build, where I've taken a very heavy car and I put very light spring rates on there, this is probably the best use case for our ability to swap air springs, aka airbags, onto any of our coilovers. Our fully threaded coilovers actually have a smooth section of that black shock body above the threads, and this allows our modular installation of airbags at any time. That smooth surface coincides with a double set of O-rings that seals the air to that black shock body. And on the top side of our airbags, it has an O-ring that seals the air against the shock shaft. So if at some time you want to actually experience the wonderful progressive nature of the air spring, then you can take off your coil springs and you can put on airbags. You can couple that with any of the universal air management systems that are available out there, or no air management system at all. If you just love the nature that is in airbags of that progressive spring rate, what you're gonna get, even if you fill up these airbags just like your tires, if you have 4 Schrader valves in the car and you pressurize those things before you go out on track to get the character that you want, as far as stiffness goes and ride height, the baked-in character to an air spring being progressive means that especially useful on a car that is very heavy and has been coupled with lightweight springs. The character that you're gonna feel with an airbag is going to be extremely buttery, small bump compliance. It's gonna have a very fast reaction and increased traction over a huge variety of road surfaces. And then when you're on track and you're actually hitting the track curbs, you're using the entire track, you might dirt drop because you make a mistake. The progressive nature up to the end of travel is like reaching your bump stop in the most gentle way. On a regular set of coilovers with just one single bump stop in there and without any careful attention paid to how much travel there is on the shock shaft, where the car is sitting at static ride height, the length of the spring until coil bind. If you don't pay any attention to that stuff when you're setting up a regular set of coilovers, when the car hits that bump stop, it completely disturbs the chassis and your line on the track. However, if you take that same track car and you put progressive air springs on there, then suddenly, in the most dramatic situations where you would be slamming bump stops on a regular coilover suspension, hitting a track curb, dirt dropping, you don't even notice that that happened. There's zero disturbance in the chassis, and that is so beautiful. Now, I think that the standard mode of operation for any track car is just to have an extremely stiff suspension versus a road car Airbags are totally uninteresting to that standard mode of operation, but the most beautiful way I think there is to set up a very confidently planted, very high traction track car is to have super soft springs, which would definitely include the natural characteristic of airbags. And then you pair that with an all solid mount, all spherical bearing suspension with some very adjustable sway bars. Now you have the best of both worlds. The sway bar reintroduces your steering response and your body roll control. And when you eliminate all rubber from the car, now when you load that suspension, it's no longer snapping back at you in the most unexpected ways. So if you go out to the track and you throw your car around and it has all the rubber in there from the OEM, when you load that up, you might start to introduce a slide, even while attempting to grip drive. Once the car starts sliding and it loads up those bushings, it'll snap back when you least expect it with an equal and opposite force. And sometimes you go to opposite lock on the steering. Sometimes the car spins out and leaves the course just because of that unexpected bounce in the OEM rubber. It's actually super sketchy, and no one's trying to wreck their car on a track day. And the most driver feedback and the most predictability, whether it's time attack or in drifting, is going to be with an all solid mounted spherical bearing suspension. Softer spring rates increase that confidence even more because the bumps that you encounter on track are getting absorbed and it's not changing the chassis attitude. So that is the ultimate suspension in my mind, is soft springs, stiff sway bars, and all solid mounts with spherical bearings. It's just the ultimate in traction and precision and control and driver feedback and response. And I want to talk about response in how we mount our sway bars. Often when you buy sway bars, you're going to buy them based on their tube diameter. Naturally, a larger tube diameter is going to be a stiffer bar. But no matter what diameter your sway bars are, they actually don't start to work until the bushings that they're mounted on have stopped flexing. So this is actually just a tragic way to mount sway bars, because the very thing that you put those sway bars on the car for, it doesn't even start to work right away. We mount our sway bars on Delrin bushings inside the bracket, in between the mounting bracket and the chassis. So we have a 50-50 C-shaped clamping Delrin mount, and Delrin is just as solid as mounting those things on solid aluminum. It has zero flex, but it does have a character that just a little grease inside there, and you can spin that sway bar like butter inside that Delrin mount. When the sway bar is mounted to rubber bushings, there's also some undesired characteristic of that progressive loading and snapback on those bushings when it comes to the sway bar twisting. So whatever spring rate is built into that tube, you're also kind of muddying that up by twisting those OEM rubber mounts. So once you have a Delrin mounted bar, then suddenly you have instant response. And just the mounts alone, regardless of the tube diameter that we choose, which is actually a skinnier tube diameter than any other bar out there, you still have instant response just because of the mounts. And that's an amazing offering from our brand. It's very unique. Another unique thing that we do is when we replace the front lower control arms, we have a series of holes going along that front lower control arm tube. And when you put your link in each of those holes ranged down the front lower control arm, what you're doing is you're adjusting the sway bar in a different manner. You are managing how much stroke from the suspension is being inputted into that bar. Now, most bars have maybe 2 holes or 3 holes for their adjustability, and those holes are arranged from front to back in the car. Those holes are a leverage adjustment. It changes the sway bar stiffness maybe 10%. But that kind of adjustability actually pales in comparison to our limit break sway bars, which typically have increased angle clearance through bladed ends and a tubular center. The bladed ends, they do start to go from the front of the car towards the front lower control arm. So they go back just like a typical sway bar. And then you'll see that we have a 90-degree bend on the end of those bars. And after that 90-degree bend, we have 3 or 4 holes for adjustability that mimics the 4 holes on top of our front lower control arm. That pairing of 8 holes horizontally, that allows you to increase or decrease the amount of stroke input into that sway bar while keeping a vertical link. The most efficient transmission of whatever's happening in your suspension into the sway bar for response, the most efficient link position is always going to be vertical. When you have a sway bar link that's mounted on any kind of angle, let's say something extreme like 45 degrees, when the suspension compresses, it's actually pushing those arms on the left and the right of the sway bar, it's pushing them in just as much as it's pushing them up. So when each wheel encounters a bump, then it's going to push the left or the right arm of that sway bar up, and then it's going to pick up the other wheel so that the car stays planted and settled and doesn't have too much roll. But as soon as your sway bar link angle approaches 45 degrees, then you've just cut that action that the sway bar is designed to do in half. So that's why it's so important to maintain a vertical sway bar link. Again, we're using bearing links. And whenever we have the opportunity to design a unique front lower control arm, if the sway bar link is ever connected to the shock, we definitely decouple it from the shock and we link the sway bar to the front lower control arm. So this gives us the stroke adjustable input, and it frees up the suspension to do what it needs to do without any influence on steering with the sway bar links that are bolted to the coilover front lower mount. When we double the steering angle in drift cars, this introduces binding in those super long sway bar links that are attached to the coilover lower mount. So to prevent binding and a bunch of load as you double the steering angle, that's another reason for us to connect the sway bar to the front lower control arm. Right now on the progression of the Tesla Model 3 build, we do not have a limit brake front lower control arm or sway bar that is Delrin mounted. It just doesn't have that series of 8 holes in order to give all that fantastic adjustability that all of our sway bar applications have and angle clearance. I'm actually looking forward to drifting the car by going to the track next time with more steering angle. And I'm definitely intrigued on testing everything out step by step, especially with the soft spring rates and stock sway bars having a lot of body roll. I think that in drifting a car where there's no clutch, I think that weight shift initiation is going to be very important to tune, learn, feel out, and it's just an indispensable tool in drifting. As soon as we have a car that doesn't have a manual transmission, then we've deleted a very important drift initiation technique. And so I need to make sure that the other forms of drift initiation, like a rally quick entry, or let's call it manji, the weight shift in the car could be an essential tool, just as essential as adding the handbrake into the Tesla for linking an entire drift course in a beautiful, smoky way. So I've talked for over an hour. I can talk all day about cars. This was prompted by Emily's simple question about spring preload. But if you're doing some critical thinking about any aspect of your coilover setup, including spring preload and how to adjust the shocks, there's just so many other aspects of settings that people don't consider, like the helper spring, the bump stop, where you're sitting at through your suspension travel at static ride height, and even the relationship between roll or anti-roll that's built into stiff springs and soft springs, and how you might marry the right spring and solid mounts and a very adjustable sway bar. Bring in all those concepts and really tune the ultimate suspension for any application, but particularly to have successful track days and an amazing ride. Thanks for sticking with me through all this. I hope that you learned a lot. If you like what we're doing around here, go ahead and show me some love by hitting the like button. Keep our motivation up by subscribing to this channel so that I know that when we put time and thought into doing videos and podcasts, that there's a consistent audience that appreciates that. Feel free to drop any questions about specific applications or additional things that you might be wondering about car setup in the comments in this video, or feel free to DM me on Instagram. Feel free to drop Tommy in the office a text message at the shop number or by email, and we'll be happy to do whatever we can to get you the right parts and get your car set up perfectly, no matter what your agenda is. Appreciate you guys.